Hello and welcome. This recording is session 5 of an 8-part series on the topic Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstobitoff. I'm a structural engineer focusing on earthquake engineering for buildings. This series of recordings is part of the MBAR initiative by BC Housing. MBAR includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. The list of 8 sessions is noted on this slide for your future reference, and that was discussed in the initial session of the full list. So today's session on cost. To start out with, this was the cost impact of a code level earthquake in BC. Again, the image on the right is taken from the NRCan website, and a link is provided later. For magnitude 9 earthquake in BC, it's estimated to have a $75 billion financial impact to BC. So again, building better performing new buildings, it will not add to this future financial impact, nor add to community disruption, nor add to community recovery time, and it will reduce the repair costs and repair time for each specific building, for these new, better performing buildings. It'll also reduce the disruption to function of a building and enable, with the goal to enable functionality rather than evacuation from a building. So what is the cost for better performing new buildings? And again, as in the previous sessions, the goal is no structural damage for these new buildings. For large buildings, in the range of 0 to 2% of the total building cost. For small buildings, up to 5% and perhaps even slightly more of the total building cost. Again, the net incremental cost really is unique for every building and really is a function of the size, the location, and the type of building. There's possible net savings in specific projects, as I'll illustrate later. So what is the benefit for better performing new buildings? Studies have shown that every dollar spent to get an enhanced, better performing new building will result in $4 saved over the life of the building. And again, there's the link to NRCan website is there for your reference. So now to a BC Housing study done in 2019. 7 existing representative buildings were looked at. They were assessed. The original code, it was designed for an importance factor of 1, a normal building, and it was compared about enhancing that design for a variety of higher performance design options. And then a cost was assigned for that. What is the cost to get to that incremental level of performance? Again, all for that one code level, full code level design earthquake. So this illustrates the 4 different levels that were considered. On the left, the building was designed by code, an importance factor of 1. And as you can see, there's 45 different structural systems available. As mentioned in previous sessions, a wide variety of performance as a result. The next one over on the right, the code post-disaster level, an importance factor of 1.5. Again, it'll be a reduced damage, still damage, and now there's some 26 structural systems available. So fewer systems available, more controlled behavior. And then for the purposes of the study, creating an area of refuge in, say, the lower 2 floors of a building where no structural damage is to occur with a post-disaster level of performance in the upper floors. Again, the intent, everybody can shelter and use the common area, and the area up above should also remain suitable for shelter in place. Or on the far right, a fully operational building, no structural damage to any level of the building. And if you design that by code, some 19 structural systems are available really to get to that level of performance. And to get to that operational level of performance as well, there's in previous sessions the use of base isolation or supplemental energy dissipations as a means to also achieve that operational performance on the right. So the results of that study, and perhaps we'll just focus on the upper table, there's an average incremental cost to achieve that far right, that operational performance level was 3.2% of the total building cost. And you can see to get to post-disaster, it was 1.1%, to refuge, an average of 1.7%, and again, as I mentioned, the operational 3.2%. The bottom table illustrates the variation depending on the concrete type, the height, and again to the various levels, and again unique for each building. These did not include any enhancements to the mechanical or electrical systems. The study followed up with a study for a particular building on Clark Drive, proposed to be built. And again, on the left-hand side, you can see there was an encapsulated mass timber or concrete tower. On the right side was a timber tower above a 3 to 4 story concrete podium. The incremental cost to improve the structural performance to that refuge, to have the podium level undamaged, was 1% of the total building cost, or to achieve that full operational level for the entire structure was 2% of the cost. We also looked at one building, an existing building. It was in Saanich, again, a 4-story timber building on over a concrete parking level. What if this was designed as a base isolated building instead of a conventional timber frame building? If the parking level could be above ground, so the isolation plane required no moat, it was a 3% increment to the original cost for a fully base isolated building. However, if the parking level had to be below grade and a moat was required, the cost of that moat and the increased detailing would increase that particular project to 6% increment to the original cost. So in a previous session, I mentioned this building in San Francisco, a new hospital, California Pacific Medical Center. In this building, early on in the design phase, there were complete parallel designs and cost estimates done for a conventional design versus a design using viscous walls. Ultimately, the viscous wall system was selected because it resulted in a net saving of approximately 25% for the steel portion of the building, and that included the cost of the dampers. And ultimately, as a result, there was a net saving to the total building cost compared to using conventional design. So as I mentioned, in certain cases, there can actually be a net savings rather than an incremental cost, very building specific. Previous sessions, I mentioned the use of a tool using P58 analysis. One of the metrics in that tool is to estimate the repair cost to restore the building and the contents to pre-earthquake conditions. And again, this is very effective to compare those two structural systems. If you look at two structural systems early in the design, you can see what the repair cost is to the structure and the components to help with the comparison of the two systems. So why aren't these higher performance buildings done every day? Why isn't that happening today? So what are some of the challenges, the barriers, the benefit versus the cost? I think in most projects today, there's a focus on the first cost budget, today's cost. What's the cost to get it built and through permitting and getting people in the building? Only some projects include life cycle costing with present value costs for designed lifespan of the building, such as 50 years or 75 years. And current life cycle costing typically only addresses operation and maintenance costs, equipment and roofing replacement and the like. But using that FEMA P58 tool on the previous slide, repair costs could be included for the probable earthquake damage that occurs over that lifespan of a building. And a link is offered there for very good guidance on benefit cost analysis by FEMA in the US. What about public knowledge as a possible barrier? Does the public understand the performance of a code design building? And we've discussed this a lot in previous sessions. Does the public believe code buildings will remain undamaged? And again, they will not for the normal code building. Does the public rely on codes to keep pace with what's available in the market and do the right thing? And unfortunately, typically the codes, do not keep in pace. And again, we're trying to do that in the National Building Code, but it's a slower moving machine than what can be done. If more information was available to the public, would they be willing to pay that 1, 2, 3% premium to buy or rent a better performing building? Again, for their home or their business. And currently, there really are no choices or ability or discussion about that with the public. And there's no market to generate better performing buildings. And I'll talk about that in the next slide. So what's happening today? There's some early adopters. There's some owners that want a higher performing building with no structural damage. And they have confidence in what that building will look like after the earthquake. And these can really serve as pilot projects for the community. As I mentioned earlier, the code, it's a 5-year cycle nationally. It'll continue to revise and improve the performance requirement for new buildings. And as such, these new buildings will be required to follow these minimum legal requirements. But again, there's, as mentioned in previous sessions, any owner can build a new building to better than code to get this better performance. The other thing is there's currently no incentives from authorities having jurisdiction to build better than code. I mean, if there were such incentives developed, such as a trade-off, perhaps an increase in height or density or parking or some considerations as a trade-off to get these no structural damage performing buildings. What about reduced insurance premiums? If you can show that your earthquake will have no structural damage and reduced damage for all the contents, can reduced insurance premiums assist as an incentive. In some countries, there's a national seismic performance rating system, such as Japan, where they give 5 stars for a high-performing, no-damage building, 3 stars for a code building, and perhaps 1 or 2 stars for an existing pre-code building. And again, that has shown to be an incentive in those countries. Perhaps that's something that will can happen here in Canada. So in summary, costs typically vary from 0 to 5% of the total building cost, and as I've shown, certain buildings can have a net savings. If possible, compare the cost of a conventional design to an improved performance design early in the design phase of a new building. Life cycle costing can show that perhaps achieve that 4-to-1 savings, as mentioned earlier. Every dollar spent in improved performance today really can reduce post-earthquake repair costs, downtime, loss of business continuity. Consider using that FEMA P58 approach to get better data on those post-earthquake repair costs. Perhaps focus more on benefits rather than cost. What are the benefits of building a much better performing building to have some certainty of being able to occupy the building and use it for its intended purpose. So that concludes this session. The next session will focus on post-earthquake habitability, all the other aspects of a building, electrical, mechanical, architectural, etc., to ensure that the occupants can stay and use the particular building. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and webpage address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.